Whenever you're ready.
Okay, so Parshi, go ahead.
Okay, great. So thank you, Kevin, for the introduction. And so I'm an assistant professor from the Department of Engineering, Science and Mechanics at Penn State University. And today I'm going to talk about 2D materials for ubiquitous electronics. So essentially what I'm going to do, I'm going to talk about what are the wide space of application of this 2D material in the electronics area. I will not probably dig into very depth of each of these topics, and I will try to give you a flavor of what are the different things that you can do with the 2D materials when it comes to electronics or optoelectronics or straintronics, flextronics, neurotronics, anti-corrosion electronics, all these different aspects. So that's what I'm going to do. So I'm going to start actually with traditional electronics. And the traditional electronics means just a normal field effect transistors. And to be honest, the traditional electronics is actually having a lot of problems because the scaling has almost ending, or if it's not at all ended, then it's almost going to end within like next few years. Okay. So we have a trouble in hand, but we have a remarkable kind of 4 decades of scaling, and which allowed us to kind of scale in 1975 with a dimension of hundreds of micrometer down to now tens of nanometer. And this has been possible with the silicon technology, and you can see the current Intel's 22 nanometer first generation Tri-Gate and the 14 nanometer second generation Tri-Gate transistors. And this has been mostly possible because our channel length has mostly remained less than this 3 times this length scale that I call the screening length or the geometric band bending length. And it kind of depends upon some of the material parameters which are listed here, like the thickness of the oxide, the dielectric constant of the oxide, and also the thickness of the silicon film that we're using as a semiconductor. Now, what has happened over the last decade is that we have kind of exhausted the P-ox and epsilon-ox scaling because we are really using ultra-thin high-K dielectric material. So that space has been pretty much well exhausted. So what is left behind is essentially the scaling of this body thickness T body, because epsilon body is the dielectric constant. You have to, as long as you're using silicon, you have to kind of deal with that number. Now, the current film technology uses the silicon film, which is about like 6 nanometer. And you can now argue that for that particular thickness, you can scale the devices down to kind of 10 nanometer. But what happens beyond that? Because the problem is, if you try to scale the thickness of the silicon film below 6 nanometer, then you run into this quantum regime where the silicon no longer remains a semiconductor because its band gap starts to increase. Okay, so that's the problem that we have in hand, which is a material limitation. And this is where we need to have the innovation in the materials. And this is exactly what makes these 2D materials very interesting, because a monolayer of MOS2 is only 0.65 nanometer thick, which means you can scale the thickness by 10 nanometer, a factor of 10, which allows you to kind of go for a few more technology nodes, because now you can scale the devices down to maybe like 5 nanometer or even 3 nanometer nodes. So that's the advantage of using these 2-dimensional materials. But the other aspect, but let me also point out this thing that when we talk about monolayers, people will always kind of try to criticize monolayer 2D materials because of 2 reasons mainly. One is monolayer has probability number, which is true. But then I don't think that is actually a concern, because if your devices are working at this 3 nanometer channel length regime, then you are mostly in the ballistic regime. So the mobility really doesn't matter. What matters is your density of states, the number of effective modes, which is proportional to the kind of square root of the effective mass. And these materials actually have higher effective mass, which allows you to actually drive more currents to them compared to silicon. And if you're working not in the ballistic limit for other kind of devices, you are in the quasi-ballistic limit. There I have some strategies to improve the mobility, because I can actually sandwich a layer of MOS between 2 HBM layers, and I can enhance the mobility by several factors. So that can actually help me to boost my mobility number. The other concern that that generally appears with the monolayer 2D material is that the band gaps are a little bit too high for semiconductor, because silicon has 1.12 eV and monolayer MOS2 is 1.8 eV. That's a little bit too large, because whenever you have a large band gap material, there is always a problem of making good contact with that material, because the contact tends to be more short through area. Okay, and that's the limitation that comes into the performance. But then there is a lot of recent work where you can actually do some phase engineering, and you can transform in the contact area this 2D material from 2A phase to 1T phase, and that has shown to give you contact resistance of the order of 200 ohm micrometer, and that number is pretty reasonable for even state-of-the-art silicon technology. Okay? So this number is really competitive with that number. But that's not the only thing. With the 2D material, what you can also do is something called strain engineering, which is very regularly done with the silicon technology. Right? With the silicon germanium, you always create the strain to enhance the mobility of your material. You can exactly do the same thing, but when you apply an out-of-plane strain to this 2D material, you can also do band gap engineering. And you can kind of see that by applying different amount of straining, pretty much all the different 2D materials, you can completely collapse the band gap and have semiconductor to metal transition. Okay, so this strain can actually help me to now get to the desired band gap as well. So really, in monolayer, I can do strain engineering to get to the smaller band gap number, and I can also do mobility engineering, which will make my monolayer actually very competitive for an ultra scale device. And to be honest, the future looks very promising, because very recently a group from Berkeley, Ali Javier's group, actually demonstrated a transistor with a channel length of only 2 nanometers. Okay, this has been already demonstrated, where they are using an MOS2 flake and they are gating it by a carbon nanotube. The carbon nanotube has a diameter of only 1 nanometer. It is a metallic carbon nanotube that can act as a gate. And because of the fringing field, you will probably have a little bit larger gating area. But this is a very interesting result where they kind of show pretty much not a lot of short channel effects, and they get very decent performance from these devices. So you can scale these devices down to 2 nanometer length, which has already been demonstrated. But then this is only one piece of device and actually being made on an exfoliated flake. If you really want to talk about billions of transistors, you need to have a technique in order to grow this material over a large area. And this is exactly what this 2DCC center is doing at Penn State, that we are looking into CVD, MOCVD in the growth of these materials, and to a certain extent it has been very successful. Right? And the challenge that still exists is that how do you integrate this synthesis on silicon platform, on that end of the line processing, which requires lower temperature, because we know that the 2D materials can be grown on many other substrates at higher temperature with very good quality and very good yield and with high mobility numbers. But on silicon, the challenge is whether you can bring down this processing temperature. So that challenge still exists. But looking at what has happened just within like 5 years of this materials becoming in the research field, it's actually very promising. So that's all good, but then the problem is that, okay, I can make a 2 nanometer transistor, what next? And in principle, that's not the actual problem that the industry is facing today. We really, on a chip, has a lot of devices that you maybe not always need for all the computation. And even the industry is also thinking towards 3D integration and all other kind of strategies. So really, it's not the idea of making more and more devices. What is more important is to make them more energy efficient, so that they consume less amount of power, right? And that's a problem which is fundamental at the device level, because all the transistors work on the principle of Boltzmann statistics, and you can only get a subthreshold slope of 60 millivolts per decade in a MOSFET architecture, right? And that is the main reason you cannot actually scale the supply voltage down, because if you want to operate this device at a lower operating voltage, you basically need to shift this black curve towards this gray curve, but you don't want to reduce the performance. So you essentially have to shift this curve because you do not want to lose your on current. And when you do that, you actually run into the problem of high leakage current. That increases your power dissipation in the device. And this is a bottleneck because your subthreshold slope is limited to 60 millivolt per decade by thermodynamics. You can't do anything because MOSFET is the top of the barrier device. Now, if you can envision a device where the subthreshold slope is actually better than 60 millivolts per decade, then you can achieve the same on current, but at the expense of much lesser leakage current and hence much better energy efficiency. And this is exactly what we kind of proposed earlier using this two-dimensional electrostatic field effect transistor, where we combine, instead of a normal dielectric, we replace this normal dielectric in the gate stack by an electrostatic or piezoelectric material. Now, what it essentially does is to first give you a layman's kind of understanding. So, when you apply a gate bias, this electrostatic or piezoelectric material goes through expansion, and that introduces an out-of-plane strain on the 2D material, and as I articulated that this out-of-plane strain then reduces the band gap of the 2D material, and it could convert this 2D material from semiconductor to metal. Now think about an ideal switch. An ideal switch should be an insulator in the off state, and it should be a metal in the on state. Right? That's an ideal switch, because then you have almost zero power dissipation in the off state, which is an ideal insulator, and you have lot of on current in the on state. And this is exactly what you can achieve by this kind of a device geometry, because now your device in the off state is kind of a semiconductor with large band gap, and in the on state it's a metal which allows you to flow a lot of current. Now let me try to explain a little bit about how this device actually operates. And in fact, the simple diagram that I showed to you may not be practically implementable, because these piezoelectric materials require higher processing temperatures, and you cannot integrate this piezoelectric on top of the 2D material, because the 2D materials are not that stable at the temperature where you actually kind of grow or synthesize this PZT type materials. So we have actually made this, what we need to do is we will first have to grow this piezoelectric, and then on top of that we are actually putting our 2D transistor. So essentially what we have done in this 4-terminal device, we have kind of decoupled two actions. One is the EFET action, which is still our normal transistor, but on top of that we are actually adding an actuator action or a mechanical action. So what really happens is that when you apply a normal gate bias to this 2D material, in a normal transistor you will just move the bands, right? And this band movement is generally given by the surface potential, and the surface potential is generally close to the applied VGS. In the ideal case, this quantity R could be 1 when you have kind of a very clean interface, and also you are having a better electrostatic control by high K dielectric. So this R could at best be 1, but not more than that. And that is the limitation which doesn't allow you to go beyond 60 millivolts per decade. But now when we are applying this gate bias to this transistor, it is also actuating this piezoelectric material. So the piezoelectric material is then expanding, and this expansion is creating a decrease in the band gap in the 2D material. And of course, you have to clamp it in a rigid structure so that whatever expansion happens to the PZT material gets maximally transferred into the 2D material. Okay, so there is some structural engineering that also needs to take place. But if you assume that I can efficiently transfer this actuation into this 2D material, then I will get an additional band movement because of a decrease in the band gap. And this additional band movement is kind of proportional to whatever pressure I can generate, the out-of-plane space I can generate, which is again proportional to the gate voltage applied and whatever is the piezoelectric material. If I choose a piezoelectric material with large Dissipation coefficient where the movement will be larger, I will create larger stress. Okay. But now the important part is that the total band movement becomes more than my applied gate bias. So I am having an internal voltage amplification. And this internal voltage amplification is something that's going to reduce the subthreshold slope below 60 millivolt per decade. So these are some of the initial simulations done by Daniel Skulman, the grad student in my group. And you can clearly see for when we assume ballistic transport, because we're really not looking into any scattering process at this point because we're really trying to understand the physics and the concept of this device. You can clearly see that depending upon the strain transfer efficiency, that is one of the parameters that we are varying, we can actually get down to subthreshold slope less than 60 millivolt per day. Now, I must articulate that you can see that the amount of amplification that we get in this device actually depends upon all three parameters. One is this strain engineering parameter, which comes from the structural part of the device. This beta part actually comes from the 2D material. If you have a 2D material which has much larger change in the band gap for a given applied pressure, I will prefer that 2D material, right? Because that will give me more band movement. And at the same time, the Dissipation coefficient, you want to select a piezoelectric material which expands more for an applied gate bias. So all this material engineering can actually take place, and we can actually even go to even smaller subthreshold slope depending upon what is the material combination we choose. And here we are only assuming 30% strain transfer. If you could do 100% strain transfer, guess that this number will be even lower. So that's the idea behind this particular device. So this is currently kind of funded by NSF, and we're trying to look into that. Now I'd also like to articulate that there are other alternative low power device ideas which also exist. One of the older one is this tunneling field effect transistor, where instead of in the on state, generally you bring this barrier down and try to have the current flow top of the barrier. But in a tunneling device, we actually want to have tunneling current. Okay, and what it does is it actually reduces the effective electron temperature, and that gives you better than 60 millivolt per decade subthreshold slope. But one of the major criticism about tunnel FET is that the on current is very low because you are actually tunneling through a large band gap, right? So the tunneling probability is going to be way less than 1, and that makes the tunnel FETs actually not that competitive with the silicon transistor when it comes to on-state performance. The off-state performance can be very superior, but you cannot get large on current. But then if you look into the tunneling probability, it actually depends on the thickness of the material that you are using for this tunnel FET. And you can immediately see that the 2D materials are the perfect choice for this kind of tunnel FET because they offer the thinnest body dimension that you can imagine. And that is why, again, for tunnel FET application, these 2D materials are also very interesting. In fact, there has been a paper from, I think Costa Banerjee's group from UC Santa Barbara, who have demonstrated that in a stack of this P-type germanium and MOS2 vertical tunnel FET, slope, so below 60 millivolt per decade. Again, cashing on the advantage of 2D material and its ultra thin body dimension. Another idea that is more ambitious, which currently we are trying to explore, is this excitonic field effect transistor, and this is where I call it extreme energy efficient electronics, because one of the holy grail of science is if you can make a room temperature superconductor, right? And room temperature superconductor, to some extent, if you can create excitonic states inside a material, then you can have a Bose-Einstein condensate, which will lead to this superconducting phase transition. Now the problem is that in a normal material, this electron-hole pair is easily recombined, and the lifetime is very short. But if you can physically separate these electrons and hole pair, but still keep their Coulombic interaction, you might be able to create excitons which can exist for longer period of time, and they have much more probability of forming this excitonic condensate, and they're giving you this phase transition. And this is something that we kind of propose, that if you have an N-type 2D material and a P-type 2D material, but they are separated by a very thin gap, because this has to be very thin because Coulomb force is dropped as 1 by r square. So if you make this distance very large, then you are not going to have a lot of attraction between the electron and holes. But at the same time, you cannot make it very thin, because if it's too thin, then the electron and holes are going to tunnel through, and the wave function is going to overlap, and it's going to lose this excitonic state. So if you can optimize these things, there is a possibility that under certain gate bias conditions, when this exciton formation could happen, you can have a phase transition in this entire structure. And if the phase transition happens, then you could get a superconductor that's very ambitious, or you could also get an insulator. But in either case, you might actually get a very steep switching, and that could help you in getting this energy efficient logic switches. But again, this is something that we are also looking into under a fund provided by Army Research Lab. Now these were all like traditional electronics, because we were trying to solve two major problems. One is the scaling problem that the silicon faces, and the other is the power dissipation or energy efficiency problem that comes out because of the fundamental device aspect. So we were trying to solve this device as well as the material innovation problem. But there is a wide application space when it comes to sensor electronics. And that is especially true with the advent of this new, or coining of this new phrase called Internet of Things, where it is kind of projected that by the year 2020, you will have billions of sensors connected over the Internet. And this is where you will need many, and what are these things going to be? These things are going to be different types of sensors, right? Electrical, mechanical, optical, thermal, chemical, biomedical, whatever you can think of. But now the requirements from the sensors are very different compared to a conventional electronic device. Because we are really not looking for high performance, right? We are not really looking for a monitoring instrument we can measure your blood pressure every nanosecond. That's not what we are looking for. We are looking for something which can measure your blood pressure every day. So it doesn't really need to operate at gigahertz speed. You can really get down to very low performance devices, but they have to be low power or self power. Right? That's an important aspect because there will be so many of them. If all of them use a lot of power, then we'll run into energy crisis. And of course, they have to be low cost because there will be so many of them. At the same time, being flexible, lightweight, transparent adds to the value. Right? With the display technology that is getting so much attention, I think these are all the important parameters to look for. And this is very different from the conventional electronics, where we really look for performance, performance, and performance. Here, we are really not looking for the performance, right? Now, in this context, what we have actually done earlier when I was in the Argonne National Lab, I was able to combine the 3 different types of 2D material, because in order to make a transistor, you actually need metal, insulator, and semiconductors. So you can pick graphene as the metal, HBN as the insulator, and tungsten selenide as the semiconductor for your channel, and combine them into a device structure which is all 2D. And if you look into the performance of this device has a mobility of 45 centimeters square per volt second for hole and 24 for the electron. And if you compare the number with the state-of-the-art amorphous silicon-based thin film transistors, these numbers are really even sometimes a factor of 10 or higher better. Okay. And still they can operate as sensors, and you can put them on a flexible substrate, right? And that makes you their application for display technology. So that's one of the area which could be also explored, because here really you are not competing with an already existing nice technology. You know, the space is much bigger to get into. In this context, we are also looking into something I call glassotronics, because we are also trying to make electronics on glass, and these are the glass substrate provided by Corning. We have a project with Corning, and this is one of my students, Joseph, who actually made these devices on glass substrate using HS2 as the top gate, and you can kind of see this nice device performance. So this is a preliminary area, but I'm saying that you can actually also make devices on glass, for example, and you can put them anywhere you want and get some electronic functionality out of those things, right? The other area, this is not something that we are working on, but I thought as a review, I should also brought these points up. For example, piezotronics is an area which is getting a lot of attention, because these 2D materials are also piezoelectric by themselves. So if you take a sheet of monolayer MOS2 and if you bend it, you actually generate electricity. Okay? And you generate electricity if the layer number is 1, 3, and 5. You don't generate electricity for the layer number 2, 4, and 6, and that's because of the symmetry issue. But again, this actually falls along the line of self-power. Trying to think of this numerous sensors which will be driven by self-energy harvesting, and you can think of putting some of these monolayer MOS2 devices on your shoes, right? And whenever you're walking, you are actually generating electricity, which can then run these devices. So these devices will be kind of self-sustained or self-powered. That's an interesting area. Now there is a lot of work that's also going on in the optoelectronics area, because monolayer of these 2D materials are direct band gap. So if you shine light, you can use them as photodetector. You can also use them for solar energy harvesting. And in fact, if you inject electrons and holes, they can recombine and they can give away light. And that will be the electroluminescence. So you can use them as like on-chip LEDs. Right? Because of course there will not be a lot of light, but that might be enough for some on-chip light sources. So that's another interesting area about this 2D material when it comes to these sensors. And then of course you can do all-purpose electronics using this 2D material. There is this is a work from MIT where they made this MOS2 bit integrated circuit. There is a work from UCSB where they made biosensors using 2D material. There are memory transistors, gas sensors, all different kinds of sensors which have been already demonstrated. So that's a big area where I think these 2D materials can really make a good way. The next topic that I would like to talk about is harsh environment electronics. Okay, so traditional sensor electronics just is going to be put into like in maybe the buildings on human body. But there is also a need for electronics in harsh environment. For example, if you're trying to put a sensor in an oil refining industry, trying to monitor the local temperature, pressure, radiation effect of the processes, because that will bring back some of the energy efficiency, because if you can really critically determine the process temperatures, that will already add a lot of value. Not only that, but you can go to, for example, if we are now trying to go to Mars, right? If you want to explore the environment of Mars, or if you want to explore the environment at the bottom of the sea, that the environment is really harsh, you need to also design electronics for that purpose. And this is where, again, I think these 2D materials may play some role, and this is some of the work that is one of my students, Andrew, is working on, is the space electronics. And in space, what happens, electronic devices actually get exposed to a lot of radiation. Okay? And the radiation could be either this Van Allen belt or this cosmic rays. There are different types, but mostly these are protons or electrons, high doses of protons and electrons that these devices have to kind of accumulate over time. So we'd like to have a material which will not kind of, or which will kind of tolerate this radiation doses. And some of our initial results actually show that if you use a 2D molybdenum disulfide transistor and expose it to a 2 MeV proton with the fluence of 10 to the power 14 protons per centimeter square, you kind of maintain the characteristics. Of course, there is a certain shift in the threshold voltage, but that's actually the problem with the oxide. That's really not the problem with the 2D material, because the 2D material is so thin, it's almost invisible to the radiation. And that's why the material is not getting degraded. It's just because we are using a thick oxide for our demonstration, and the oxide is getting affected. And then the same thing happens, and this is actually a typical dose that a satellite will accumulate over 1 year. 10 to the power 14 protons is a typical dose. But we are also a little bit ambitious. We also tried heavy ions like helium with very, very high fluences. And of course, at that state, things start to degrade. But our initial assumption is it's probably not the 2D material. It's mostly the oxide that is getting damaged, and that's why we're not getting any kind of gating action from these devices. But again, that points, this result actually points to the idea that this 2D material can be implemented for harsh environments like this space application. The other thing that I think which kind of came out of some accidental discovery that happened when I was working in the Oregon National Lab is that these 2D materials could act also as anti-corrosive electronics. Means for example, if you want to monitor chemical processes, then you might want to put sensors inside chemicals, and you don't want those devices to degrade with those chemicals, right? So you need something that will survive like toxic, oxidation, or corrosive environments. What we found is that when you take these multi-layer 2D materials and put them on a titanium nitride substrate, and then you do some electrochemistry where you actually apply a very large positive potential, where you generate a lot of oxidative species like hydrogen peroxide or other oxidative species, we found that the multi-layer flakes are actually converted to monolayer. And that actually happens for pretty much most of the 2D material. You start with a multi-layer flake, you just do this corrosive process, and the monolayer survives, while the bulk material actually disappears, which shows that the strength of this monolayer in this corrosive environment. Now let me explain a little bit about what's really going on. Why do we have this monolayer surviving in the corrosive environment while the bulk layer is gone? What we believe is that when you exfoliate a material, these 2D materials on a substrate, the layers which are lying on the top are connected by van der Waals force, right? So this is very weak force, and the energy is generally of the order of 0.16 eV. But because of the exfoliation process, there is some interaction that takes place between the substrate and the 2D material, which is much stronger. And these are some calculations which are done by my colleagues from the Oregon National Lab. Now, generally, these 2D materials are very inert in the basal plane. So nothing actually happens from the basal plane direction. The chemical is chemically very inert. But the edge sites are the one which are defective, and that's where all the chemicals start to attack this 2D material. Now, you can see in this temporal evolution of the AFM images is that at the beginning I have a flake, and as the process proceeds, I am kind of etching this material from the side. So it's from a side to center etching, but then miraculously this last layer survives. So what happens is that in the last layer, your edges are interacting strongly with the substrate, and now the edges also become inert. So your basal plane is already inert, your edges are now also inert, so you cannot really etch this monolayer. And that makes them so much superior when it comes to electro-oxidation and corrosion processes. Right. And then we, of course, did a lot of characterization to figure out whether these layers which are left behind are actually monolayers. So we have all the Raman, PL, and the TEM showing that these are actually monolayers. And in fact, what could have happened, because we all know when you treat these 2D materials with chemicals, there could be phase transformation. You could have gone from 2H to 1P phase, and then that will be a semiconductor to metal transition, and that you do not want for electronic device application, right? You still want to preserve this 2H semiconducting phase, and the TEM actually confirmed that. But then for device engineers like us, we kind of really want to make devices and make sure that it is really a semiconductor, and these are those ID characteristics of monolayer 2D materials which have gone through this extreme corrosion process, and their performance is at par with what you will get from exfoliated material, which is pristine. That kind of lays the kind of your background for anti-corrosive electronics using this 2D material. We have also worked a little bit on looking into the reliability of this 2D devices. How am I doing with the time? Good. Okay. So look into some of this hot electron transport in these 2D materials, and that's again some of the work that is done by Andrew. So here what we did is we actually stressed these devices. So generally you won't apply like this high drain biases to a normal transistors. So there's some information missing. So these were like 500 nanometer channel length devices, and these are the same monolayers which have already gone through this extreme corrosion process. Okay. Now we're taking these monolayer devices and applying extremely high voltage across them and trying to see how far we can stretch the voltage limit of this 2D device operation. Now you can see that if we bias this device in the off state and then apply this large tracing voltages, you start to see a little bit of shift from the threshold voltage in the negative direction. But then it can be very quickly recovered. If you wait for a certain period of time, the device actually gets back to its original state. Now, if you do the same experiment, but in the on state of the device, then you kind of start to see again the similar effect, but something drastic happens at 10 volts in the on state. And that's because of the fact that you have a different band alignment or band structure. I'm coming to that in the next slide, what's really going on in these 2D transistors when you apply these high drain biases. But when there is and this change is very abrupt, right? Now the threshold is shifted way towards the negative. And from this, it's very difficult to recover the device. In fact, we couldn't recover it by waiting for a day. But then the next step is something we call the curiosity-driven stressing. We didn't still stop. The device was almost like not working. But we still kept increasing this drain biases. And then we found something again abrupt happened at the 18 volt, where the threshold now shifted from very large negative to very large positive. Okay, so which means that in this case now we are injecting electrons, because here if you have a negative shift, as I will tell you, this is hole injection into the oxide, while in this case it's electron injection into the oxide. Okay, and this is how the device starts to degrade, and you can see the electron injection is much more detrimental because now the on current dropped quite significantly, and it also introduces certain amount of interface trap states, okay, which was not happening with the other stressing mechanism. And this is what we call this hot carrier transport. So when we apply a large drain bias, you kind of create extremely large electric field at the drain end. And what really happens for an electron which is nearing this drain edge, it will gain a lot of energy from that field. And when it gains a lot of energy, it actually becomes hot. Right? Now once the electron becomes hot, it can actually go through several processes. One of the processes is that it will actually collide with another electron, where it will not lose its energy, but its momentum will get randomized. Now once its momentum gets randomized, it can become a lucky electron, and it can get injected into the oxide and get trapped inside the oxide, and that will lead to a positive threshold voltage shift. Okay. The other phenomena that could happen is that it actually collides with a lattice and creates a new electron hole pair. Now the newly created electron hole pair, the electron from that pair could again become lucky, and it could go through the same process and again get injected into the oxide. But the same thing could also happen with the holes. That the holes could also become lucky and eventually get trapped into the oxide. But in this case, we'll actually get a negative threshold voltage shift. So the threshold voltage shift points to the direction what is the actual phenomena that is happening, right? And the third alternative is that they don't do anything, they just keep multiplying, and in that case we'll have an avalanche process. And this to a certain extent, if I go back in the last slide, I don't know whether I have it in the next slide, you can clearly see that when I'm in the off state, I'm injecting holes because I have a threshold shift which is in the negative direction, when in the on state, I'm getting more of an electron injection. And this kind of studies are very important to understand the reliability of this 2D material, how far you can stretch or bias these 2D materials. Okay? And this could be used again for like harsh kind of conditioning of these devices. And the last one that I'm going to talk about is this brain-inspired electronics, and that is something for fun that we do, okay? Because there is this huge topic of neuromorphic computing and all these areas that are emerging. Although I don't know, means there is a lot of understanding that has been well developed. So we thought we'll do some experiment for fun in this area. You know? Now, one thing which is very important when we talk about brain and compare it with a computer is that in a computer, your logic module is separate from your memory module. You know, your logic operations are performed independently of the memory, and the memory really doesn't dictate what will be. But that's not how the human brain works, right? Because in human brain, your action is determined by your experience. So whatever you have learned is going to determine your logical action, right? So the same person can behave very differently given the same condition, but based on his past experience. So you need to kind of intertwine this logic and memory in a device in really order to capture what happens in human brain. So that's an interesting aspect. And what we specifically tried to do, because if you look into the how the signals are processed in human brain, is essentially through these chemical synapses, so where you have an action potential which propagates to the axon, and once it comes to these chemical synapses, it actually releases neurotransmitters, and this neurotransmitter actually then gets bound to the next receptor molecules of the next neuron, and then they kind of start some extensive molecular procedure which actually generates a signal in the next neuron. So that's how you kind of propagate one action potential from this neuron to the action potential in the next neuron. But of course, there are multiple connectivities. But at the essence of this neural information processing is this neurotransmitter release. Because neurotransmitter release dictates whether you will propagate the signal or not. So if you can mimic this neurotransmitter release by some device action, that could actually be an interesting aspect in realizing these neuromorphic devices. Now, this neurotransmitter release actually has three essential features. One is that it's a quantum release, which means that each of these vesicles contains a specific number of neurotransmitters. Okay, so when one of the vesicles is released, you get a certain amount of postsynaptic current or postsynaptic potential. And the increasing form of quanta, because you can release one vesicle, two vesicle, or three vesicles. So they are quantum in nature. The next is just stochastic. Means even if an action potential comes, it's not necessary that the neurotransmitter will be released. So there is this stochastic nature which is also inbuilt. And this is also another aspect which we are trying to bring in our normal computational paradigm. Stochastic computing you will heard many times nowadays. And neurons actually does it very often. So it's a stochastic process. And finally, it's a bipolar because this neurotransmitter could be either excitatory, where they are actually promoting the signal to propagate to the next neuron, or it could be inhibitory, where they are actually not allowing the signal to propagate it to the next neuron. So these are the three essential features. And what we actually did using our backdated MOS2 transistor, we tried to capture this neurotransmitter release. So here we are actually replicating a neuron by saying that my VGS is the input synaptic terminal, while my drain is actually the next neuron, where I get the output in the current, right, which is the postsynaptic current is obtained at the drain terminal, while the inputs or the action potential come with the VGS. And this is a typical device characteristic that you will find for the MOS2 transistor. But what is more interesting is that these devices are not ideal, you know, and this non-ideality is something that is inherent in like we are not ideal. And what happens is that in a normal transistor, if you want to operate this as a logic transistor, you want to avoid this hysteresis, right? Because hysteresis is not good for logic. Hysteresis is good for memory. But because of having not the perfect interface between the 2D material and the silicon dioxide, we always get this hysteresis, which means that these devices have both logic as well as memory inbuilt in them. And what has happened over the years is that we have made the silicon devices so nice that we have kind of separated these two effects. Now these effects come automatically with this 2D material, and you can see that depending upon what is your drain voltage, or the gate voltage that you are applying, your hysteresis width actually changes, which means now the device has a memory. It remembers whether you have applied minus 60 volt or minus 40 volt, and that's how its characteristics changes. So it has got a memory now. And it's the same with the fact that whether you do a slow sweep or a fast sweep, your hysteresis also changes. So depending upon the temporal and the voltage input, you can change this thing. But I will not go into the much more detail, and I will just articulate where is the origin of hysteresis, because the hysteresis comes because our 2D material is not ideal. You know, there is an interface with air, and we can have adsorbents in the 2D material. Our interface with the silicon dioxide in the back gate is not ideal, so there could be interface trap state, and the 2D material by itself also has defect sites. So all this could give rise to this non-ideal things, but I'm saying that we always look for optimizing or making these materials better, but maybe we can work with a crappy material which will give us this neuromorphic action. You know, so that's kind of the philosophy behind using these materials for neuromorphic application. And then what we found is that if we actually input these action potential type pulses to these synaptic terminals, to kind of replicate what the neuron does. Okay, and we can, I'm not going into the detail of that, but you can essentially capture the quantal release by the pulse, number of pulses that you are applying. You can do the stochastic by the time of the pulses that you are spending, and the bipolar nature is just because of the nature of the transistor. Okay, so this is what we have, and if you want to read more in detail, so Andrew has already published this paper in ACS Nano, so you can read this thing. So this is all about the brain-inspired electronics, but this is kind of, I said that we did it for fun, you know, and there will be many questions that could be asked, how do you realize a neuron? But that's just a small step towards kind of achieving this neuromorphic computing. So that kind of brings me to the summary of my talk today. So what I kind of tried to capture is that 2D materials seems like they can reinstate the scaling, which the industry is very much interested in, but compared to scaling, what is more important is like this low power energy efficient devices. And what I tried to convey the message is that you can have these novel devices like this electrorestrictive FET, tunnel FET or EFET, which are much easier to implement with this 2D material, and that makes them more for application. And then of course, if you looking into IoT type of devices for all purpose sensors, then of course these 2D materials could be very useful. They could be useful for harsh environment electronics in mining, in oil industry, and also this brain-inspired electronics could be captured by these 2D materials. So at the end, I would like to acknowledge all the funding sources, the Air Force Office of Scientific Research, who provided the support to this young investigator program. NSF and SSC jointly funded this electrorestrictive FET idea under this E2CDA, Energy Efficient Computing from Devices to Architecture grant. And the Army Research Lab, which showed some faith on these exotonic devices through this short-term innovative research grant, and of course Corning, because we are working on this glass substrate. So this is my group currently, and all the faculty collaborators inside Penn State and even external. So thank you, and I will get any questions.
So we do have a question online. First of all, I said thank you, very comprehensive and educational, which is exactly what we want in this series. So we have a huge mixture online and on site. We have graduate students, we have late career scientists, early career scientists. So this is actually a very good talk for Pressure, so thank you so much. The question was, for slide number 25, what is the evidence of covalent bonding or binding between looks like MLTMD and the substrate?
That's an excellent question, and I think that's at the hypothesis stage. And this is something that the simulation folks did the DFT calculations, and they showed that the binding between these the substrate and the last layer of 2D material is actually stronger than the van der Waals forces. So what I could also say that we have done now some extensive experiment where because it's always very difficult to believe that when you do this normal exfoliation process, you are essentially just pressing it with your thumb. and the thumb pressure is actually very small, how can that small pressure lead to a covalent bond? Because formation of the covalent bond is a very difficult process. But what we have found actually in some experiment done in the advanced photon source in the Argonne National Lab is that the local strain that can get created in these materials, even when we are doing this exfoliation process, could be of the order of gigapascal. Okay, and that could lead to some of this covalent bond formation while the exfoliation process is going on. But then that is still at the speculation stage. I would say that this is still at the hypothesis stage. There could be something more funny going on with the chemistry. I'm not an electrochemist. What I care about is that I take a 2D material which is bulk, I put it in a solution, what I get is monolayer, and that I can use for my electronic application. So answering that question probably would require much more in-depth kind of investigation into the chemistry of the processes, which we are trying to do now, but not at convincing comment that why is this process happening.
Any questions here on site while we get more online? Please go ahead.
Yeah, so my question is about the straintronics that we're talking about.
Mm-hmm.
You take a single monolayer and you strain it using a piezo. So, slide 8, 9,
yeah, I think
around
it is.
there, this amount of strain you get is gigapascal or something?
No, not this strain. This is actually much smaller. So here when you're, so you can see the numbers here, right? So the numbers that we got, the current is like 20 picoamps, or the voltage that you are generating for monolayer, I think it's around like 20 millivolts. That's very small voltage.
No, I'm not talking about this one. There's another one, 8, 9, 10, somewhere around there. Slide number. Yeah.
Oh, here, yes.
These ones. So these you are growing, right?
So our device structure would look something like this. Okay.
And what is the strain you're getting?
So the strain you can get is, now if you do a back of the envelope calculation, means generally the D33 coefficient for these electrostatic materials, if you have a very good electrostatic material, if you do some structural engineering, is 1 nanometer per volt. That's a typical number. So if you apply 1 volt to the gate, you can have 1 nanometer displacement. Okay. Now, if I also assume that my capping layer is perfect, right, nothing expands. So then this 1 nanometer strain will be transferred into this 2D material. Okay. Now my 2D material, its thickness is 1 or 2 nanometers. Okay. And you are compressing it by another nanometer. Even if I get 30% strain transfer, you will be contracting it by 30%. That's a huge amount of stress. That kind of correlates to this amount of pressure.
Second question is, what is the largest that you can make these devices, like in the X direction?
Very good question, and there are many subtleties with this device. One thing that is also very important is that the area of this device has to be actually much smaller than the area of this electrostatic material. Okay, and that's like this hammer and nail principle. If you want to transfer a lot of strain, you really need a nail, and you have to hammer it. So this has to be our hammer, and this material has to be our nail. But then scaling is not a problem with the 2D material. We can make it very small. But when it comes to the integration density, then this device might actually lose a little bit of space, because now I have to sacrifice some space in order to accommodate this large area of this piezoelectric material. So I don't know whether I answered your question.
So, can you give like micron, 10 micron?
So generally I think some of the calculations that one of my students, Daniel, has done, it shows like if you have a ratio of 1:5, then you can probably get almost like 10 to 15% strain transfer efficiency. So that will be a typical number, but those are very initial simulation. I didn't show them here because those are still at the stage of refining and we're trying to understand.
Question online. Can you go back to slide 9, please? So basically, we have a question about pressure-induced semiconductor to metal transition. And what was the TMD compound, and is it 2H to 1T phase change? Is the question.
No, it's not the 2H to 1T phase. Yeah, I didn't talk about that. So what is really happening is when you apply this out-of-plane pressure to this 2D materials, you essentially decrease the air gap between the consecutive layers, because there is an air gap which is holding these 2D materials together. And when you decrease this air gap, what you are essentially doing, you are changing the overlap of the atomic orbitals, and that's changing the band gap.
Okay. So we have a follow-up online here. On slide 10, so your next slide, is the strain on vertical out of plane direction or lateral in plane?
It is vertical in direction mostly, but of course, if you have a vertical compression, automatically the device will have a lateral impact. So, but we need this strain in the vertical direction, out of plane direction.
So maybe we can wrap up with one or two questions here on site, and then we'll be on time. So, Slava?
So following up the questions that you had, so this bandgap engineering by strain, what does it do to the off-state and on-state current? So probably it changes both.
So the off-state current doesn't change because in the off-state you're not applying any voltage. So I have a band gap of, let's say if I'm using a monolayer or a bilayer, 1.8 eV, which gives you a really low off current. But once you start applying the voltage, you're actually then starting to reduce the band gap and you're going towards the on state. So your on current becomes higher. The off current still remains the same. You increase the on current and you reach to the on current at a much smaller applied VGS than you will get in conventional EFET.
Maybe one more? One more question? If not, thank you so much, Saptarshi.
Okay.